So, let us look at this idea now. Let us assume that I have a process here which is like most processes is truly multivariable. So, the way I have shown that this process is truly multivariable is that there are two inputs that come into this process block and there are two outputs y1 and y2, and then you see there is a path from u1 to y1, path from u1 to y2. That means, whenever I change u1, both y1 and y2 get affected. And similarly, whenever I change u2, both y1 and y2 get affected. So, it is truly multivariable. However, typically what we have been doing is we have said, okay, let us look at u1 being manipulated to change y1 and u2 being manipulated to change y2 and so on. So, that is clearly not possible. It is not possible most of the times, but we still have ignored this and then said whatever is the effect of the other loop, I will handle that as disturbance and so on, which is what I have told you at the beginning of this course. But now let us see whether there are any better ways of doing this now that we are used to using a model of the process with the controller implementation, starting from the controller design for time delay systems and so on. So, we are really looking at seeing if there is any better way of handling this while still retaining the basic single input single output structure as far as tuning and other things are considered. Okay. So, this is the idea that we are looking at. So, basically let us assume that somehow we are going to get output which are decoupled in some sense. So, I have one output which is called y1 decoupled, another output which is called y2 decoupled, and we are going to do some transformation. So, that when I look at the outside, I am going to manipulate u1 decouple to control y1 decouple and u2 decouple to control y2 decouple. Okay. So, basically what I want to think about is there are still two seesaw loops. If you kind of combine all of this together into, let us say, one process, if you look at this, this will look like a single input single output feedback loop, and this will look like a single input single output feedback loop. So, is there some way in which we can define u1 decoupled, u2 decoupled, y1 decoupled and y2 decoupled in such a way that from the outside it looks like a single input single output controller, so that I design my controller for only this is what we are trying to do. So, the way we do this is the following. So, what we do is ultimately the true manipulated variables are u1 and u2. You might say, okay, I am doing computing u1 decoupled, u2 decoupled and so on. You could go ahead and compute that, but even then you still need to figure out what u1 and u2 are in actually in the controller implementation situation. Okay, because those are the physical manipulated variables. So, supposing let us say I have come up with some u1 decoupled and u2 decoupled, which I will show you how we come up with. Then I might say, if I am going to recalculate u1 and u2 from these, so then I could come up with some linear transformation. So, I might write this equation like this u1 u2. This is ultimately the final values I need to keep for the true manipulated variables. I might say, okay, I have di 1 1. So, this is the input decoupler, that is the reason why I use a superscript I, and 1 1 you will see what that is, di 1 2, di 2 1, di 2 2, and then I have u1 decoupled input, u2 decoupled input. So, this might be a standard form. So, basically what this says is I have computed this u1 decoupled and u2 decoupled somehow, and I have really have to convert that to true inputs u1 and u2, because those are the physical inputs. So, since I have these two, I am going to take a linear combination of these two, and I am going to take a linear combination in a particular way that makes it useful for us. Okay. So, typically u1 will be di 1 1 u1d plus di 1 2 u2d, and u2 simple matrix multiplication. So, you will write it like this. So, u1 u2 equal to di 1 1 u1 decoupled plus di 1 2 u1 decoupled and di 2 1 u2 decoupled plus d u2 decoupled. So, this is your matrix multiplication this way and this way, right. So, you get this. So, you notice u1 and u2 are written as linear combinations of u1 decoupled and u2 decoupled. Okay. Now, we have 4 things to choose, which is di 1 1, di 2 2, di 2 1 and di 1 2. what we are going to do is, for the sake of convenience, let us assume that I choose this as simply 1 and this as 1, okay. And you could have chosen something else, but for ease of computation we are going to do this. And so that gives you this matrix form here: u1 u2 1, di2 1, di1 2 1, u1 d u2 d. Now if you do the same matrix multiplication, just this di1 1 and di2 2 will become 1, the other things will be the same. So I will have the true physical input u1 as u1 decouple plus di1 2 u2 decouple, and u2 as u2 decouple plus di21 u1 decouple. Now from a process viewpoint, also we have this decoupler. Let us assume that same way I can compute this y1 decoupled and y2 decoupled as a function of y1 and y2. The simplest choice is to not do any decoupling here. You do not really need to do that, you can do other things, but the simplest choice is what we call as an I matrix. So basically if you think of this y1 decoupled, y2 decoupled again as some output decoupler matrix. The other matrix I showed in the previous slide is an input decoupler matrix. If you think of this as an output decoupler matrix multiplied by y1, y2, now you can set this as identity. Identity meaning you are not doing any decoupling as far as the output is concerned, in which case you will get y1 decouple equals y1 and y2 decouple equals y2. So that is what you will get. So basically what we are saying is there might be reasons and there might be cases which are more advanced where you might actually choose a D output so that it makes some things better. But as far as the simple cases are concerned, we can simply set D output equal to I. Basically that is equivalent to saying y1 is y1 decoupled, y2 is y2 decoupled. Okay. Now also notice there will be a transfer function between y1 and u1 and u2 and y1, and there will also be a transfer function between u1 y2 and u2 and y2. So there are 4 transfer functions which are the true transfer functions which have already been identified. So we will use that. Okay. So as far as this picture is concerned, for this decoupler module, though there are 4 elements or 4 components I can choose, I am going to choose 2 as 1 and the remaining 2 are yet to be computed, which is what happens with this D input side of the decoupling. The D output I am simply going to assume its identity. So I will simply get y1 decoupled is y1 and y2 decoupled is y2. So we come back here. Now we write u1 as a function of you will write y1 as a function of u1 and u2, and you will see that typically in a multivariable process which we have seen before. So if I have y1, there is one transfer function g11 for u1 and then one transfer function g12 for u2. Similarly you will have y2, you will have one transfer function for u1 and one transfer function for u2, which is what we have written here. Let us look at what we do with y1. What we are going to do is this u1 we are going to substitute from here. So y1 is g11 times u1 decouple plus d12 I u2 decouple, plus for this u2 we are going to substitute this here. So this is going to be u2 decouple plus d I21 u1 decouple. So very simple resubstitution. Okay. So this will give you y1. Now I can collect all the terms corresponding to u1 decoupled and u2 decoupled, and I will get a form like this where there is some transfer function times u1 decoupled plus another transfer function times u2 decoupled. Now if I asked you, since we have the choice of g12 and d21 and d12 in our hands, okay, so how do I choose these so that we get some benefit out of doing all of this, is a question that we might ask. Now if you look at this equation and if you look at the picture before, okay, now we know this y1 decoupled is y1 because we have not done any choices for this other than saying this is identity. So clearly y1 decoupled is being controlled by manipulating u1 decoupled. So in an ideal situation, what we would like to have is make sure that this u2 decoupled has no impact on this loop, and similarly u1 decoupled does not have any impact on this loop. That basically means, can we decouple these inputs in such a way that y1 decoupled is not a function of u2 decoupled and y2 decoupled is not a function of u1 decoupled. So, that is a basic idea. So, again let me repeat, y1 decoupled is y1, y2 decoupled is y2. If we want to really decouple these loops, basically what we are saying is, I want to come up with u1 decoupled and u2 decoupled in such a way that u1 decoupled has only impact on y1 decoupled, no impact on y2 decoupled, and u2 decoupled has only impact on y2 decoupled and not on y1 decoupled. So, that is a basic idea. Now, if you use that idea, then we are saying y1 only u1d should impact, u2d should not impact. So, if u2d should not impact, then that means that this has to go to 0. Now, this is a fixed part of the process transfer function, this is a transfer function which is known. However, we have introduced this here which is in our hands. So, this is something that we can choose. So, if we choose that, then you will get this equation here for one of the decoupled matrices, and similarly if you look at y2 and do the same algebra now, y2 is a function of both u2 decoupled and u1 decoupled. Now, if you want y2 to be affected only by u2 decoupled, then what you would say is you want this to go to 0. So, that will give you one equation. Here again this is known, and this is something that we can choose. So, once we decide that we want to make this to 0, then the choice for that is also obvious. So, from this I can get these two decoupling elements, which if I put into this overall di. So, I have 1, 1, and this one I have computed, this one also I have computed using these two equations. Now, I have an input decoupler. Now, if you simplify this in terms of transfer function only for u1 decoupler, then you will get y1 equal to g1, now a slightly different transfer function from before. So, initially if it were u1, this will just be g11, but because we are going to correct for the effect of u2, this transfer function becomes this transfer function. Similarly, this transfer function becomes this transfer function. Now, if you notice these two equations, it looks as if y1 is only affected by u1 decoupled and y2 is only affected by u2 decoupled. Okay. So, we have essentially got two single input single output control loops. So, this is what is called complete dynamic decoupling, and notice how we are starting to use the model more and more. If I had built a model for these 4 transfer functions, I am going to modify the transfer function between y1 and u1 decoupled through this formula here, and similarly I am going to modify the other transfer function for y2 and u2 decoupled. So, that way you now have written two single input single output loops. You can use the standard techniques that we have been using to compute the controller coefficient and so on. So, there is nothing which is difficult to do here, because all of these are transfer functions. We know how to work with these transfer functions. So, basically what will happen is we have already identified this D input decoupler. So, in a real implementation, let us say there is difference between y1 and y1 set point, that will go to the controller. So, the controller will decide what this u1 decoupled value is. Similarly, the difference between y2 and y2 set point will decide what this u2 decoupled is. So, that just figures out what this and this are, but in a real implementation what you need to really do is actually go and manipulate u1 and u2. You cannot manipulate u1 decoupled because that is not a physical input, that is an input that we have constructed. However, we know that the true physical inputs u1 and u2 we can actually compute as this input decoupler matrix times u1 decouple, u2 decouple. Now, this and this are already given by the controllers here and here based on the error. Okay. So, once we have this, we can actually have u1 and u2 which will be implemented on the process, then you will get a y1 and y2, check it with respect to the set point and then keep continuing this process. Okay. So, if you think about really what the controller is, okay, there seems to be there are two single input single output controllers, but if you really think about, this is an identity matrix, right. So, basically if you think about combining all of this together into one block, then you could say there is a process block, okay, from where y1 and y2 are coming out. This is being compared with this corresponding set points, the error is going, and then there is one controller block, but this controller block has two blocks inside. One is a decoupler which gives you this, and before this decoupler there is a C1, and before this decoupler there is a C2. So, you can think of this whole thing itself as one big block, which is now the controller block. Because of the decoupler, everything gets combined together. So, this is really your multivariable controller, which has two single input single output controllers and a decoupler, and then this really gives you U1 and U2, and from here you get, by comparison with the set point, you get the two errors E1 and E2. So, there is a comparative block here which gives you the errors, and that comes into this multivariable controller. However, the beauty of this is because we have done this, these controllers can be designed like a single input single output controller. Okay. So, again the notion of including interactions is beautifully addressed here, where we choose our decoupling matrix in such a way that we have a minimal effect or zero effect if the models are perfect of U1 decoupled on Y2 and U2 decoupled on Y1. Now, you will also notice that this is very similar to how we looked at feed forward control. So, you might think of this as a generalization of the feed forward idea. Remember, in feed forward control also we had two terms for the Y, where there was one term which was coming from the disturbance, and then we said if you want to kill the disturbance, what should that be? So, we set that term to 0. Now, in this case for Y1, we notice that if we assume that I want to only be manipulating U1 decouple for Y1, then the effect of U2 decouple should be 0, just like how we said in feed forward the effect of disturbance should go to 0. So, that basically means that this transfer function had to be set to 0. And similarly, when you talk about Y2, again we want only U2 decouple to have an impact on Y2. So, the transfer function which is multiplying U1 decoupled was set to 0, much like how we did this feed forward. So, what we initially at the very beginning of this course talked about in terms of being able to think of the inputs from the other loops as being disturbances to the main loop and so on, how we actually treat that mathematically and how we actually make sure that the effect of the other input goes to 0 is seen now after several lectures and through a progression of ideas. Also notice that the models are being used more and more in these cases, and we have started to see truly multivariable control. However, I also want to emphasize that once we have understood this single input single output control quite well, then you can see that lots of these are primarily extensions of that idea. So, once you have a basic grasp and very good understanding of this single input single output controller design concepts, then you can keep adding on to that in terms of how you think about multivariable design concepts. The other thing that I also want to explain here is now you will see the power of Laplace transform. So, if you had to do all of this in time domain, then you have to really worry about how you are going to decouple this input from the other one. You will have integration and complicated cancellations in integrations and so on. Because all of this has become algebraic when we start working with Laplace transforms, you see a transfer function and another variable multiplying the transfer function, and if you want to get rid of the effect of that variable, we simply set the multiplying transfer function to 0, which is a simple concept. And the way we get these transfer functions for y1 and y2 themselves are simple algebraic manipulations. And so, lots of other things that we are doing here in terms of decoupling and so on all get completely merged in some simple algebraic transformations which are very easy to understand. So, I hope you got a good idea of how you do this for 2 by 2. Now, if you have 3 by 3, it is the same idea, there is nothing particularly complicated there. When it comes to a 3 by 3, let us say, then y1 will have the effect of u1 decouple, u2 decouple and u3 decouple. So, if you want only u1 decouple to affect y1, then the transfer functions which are multiplying the u2 decouple and u3 decouple you will set them to 0. So, there will be 2 choices there, and then with respect to y 2 similarly you will have 2 choices which you have to set to 0 corresponding to u 1 decoupled and u 3 decoupled, and for y 3 you will have to set again 2 transfer functions to 0 which will be corresponding to u 1 decoupled and u 2 decoupled. Now, you will make those 6 choices, and remember if it is a 3 by 3 matrix there will be 9 elements in the 3 by 3 matrix. We will again do all the diagonal elements to be 1. So, 9 minus 3 6 choices, that will be those 6 choices that I just talked about, and then you will have a decoupling matrix, and you can continue this for 4, 5 variables and so on. This is one simple way of thinking about multivariable control, which is very useful from the viewpoint of understanding how some of these are done. So, in the next lecture I will continue on these ideas, and till now we have always said a particular input will be used to control a particular output whenever we talked about CISO, and even when we came to cascade control we still had a particular input that is used to control a particular output. Even in feed forward control we had a particular input which will be used to control a particular output, and surprisingly even in this multivariable case we had a notion of what input is going to control what output. That is how we set the other decoupled input to 0. So, in every case we always have some inputs which are used to manipulate some outputs, and at the beginning of this course I talked about these choices. So, supposing if I have let us say 5 control variables and 5 manipulated variables, which manipulated variable do I match with which control variable is something that we have never talked about. So, what I am going to do is in the next lecture we are going to talk about that, and that will kind of end this whole sequence of transfer function based multivariable control or more traditional advanced control ideas. I have left that to the end because now that we have understood all of this, just that one part if I teach in terms of how do you make these choices about which variables to pair, then that will kind of complete the circle of arguments that we have been using till now. And one thing that I have been mentioning is as we go through multivariable control we use the model more and more. So, that is something that you want to keep in mind. Now, there is a notion of performance in direct synthesis controller. There is really no notion of performance, but still there is a notion of stability and then back off in traditional stability based controller tuning and so on. However, in both these cases there is no explicit optimization of metric online from a control viewpoint. So, that is what is called as model predictive control. So, after I teach my next lecture on how you do this pairing, we will move on to a truly optimization based control where there is a performance metric that is optimized in every controller calculation. So, that will be the first time you will see that you will not have direct analytical relationships, but the input itself will be a solution to an optimization problem. In some cases you can actually write that as a direct analytical expression. In other cases you have to get to do things that are more complicated before you can write the controller manipulated input as a analytical expression. So, we will discuss all of this as we go through more lectures on this multivariable control. Thank you.